Ja, välkomna hit allihopa. Till vårt, blir det nu ett andra möte är det ju i år. Va? Och hoppas att ni tycker ni har hittat rätt nu när ni har hittat hit, men det tycker ju klart vi. Det finns också en del ute på nätet. Ni är också välkomna. Jag ser 13 stycken för närvarande i varje fall. Så att vi har ett förhoppningsvis trevligt program. Jag hoppas att ni alla har fått den här dagordningen eller kallelsen. Och då vet ni vad som väntar er ungefär. Annars så ser ni det här. Som vanligt så gör vi så att vi hälsar kvällens huvuddragsföredragare. Hjärtligt välkommen. Och kan ni bli lika förvånad varje gång. But Jens, if you rise, you will have a welcoming applause. We always do this to surprise the speaker. So very much welcome, and we're looking forward to your talk a bit later. Now, back in Swedish, föreningsnytt då. Där hade jag faktiskt tänkt att vi skulle få höra lite från dig, Peter, vår astropedagog. Och om du kopplar på din mikrofon så får vi kolla att du hörs.
Precis, jag ska väl höras nu.
Då ska vi se, ja det funkar också. Ska vi se om vi kan se det också. Men det är lite oklart. Ja, se där. Där dök du faktiskt upp. Jättebra.
Ja.
Och så ska vi också dela på en liten PowerPoint. Då ska jag försöka göra det här på bästa tänkbara sätt.
Det kommer att gå bra.
Det är nämligen en särskild konst. Och sedan kör vi
där, ja.
Där. Och sedan så gör man om det där nämligen. Eller så, jo, eller hur? Och sen kan man dessutom, tror jag, göra så. Så, jättebra. Välkommen Peter. Alltså,
tack
du
så
är ju
mycket.
astropedagog och är ju aktiv med barn och ungdomar i första hand. Och nu har det varit en hel del sådan verksamhet och vi har ju ny verksamhet. Och berätta nu lite grann om vad som har hänt den senaste tiden. Varsågod.
Ja men absolut. Jag kommer att avsluta med vad jag har gjort idag som inte har haft möjlighet att ha med i bild. Jag håller alltså i föreningens barn- och skolverksamhet. Det vi ser här på den första bilden, det är från en av måndagsvisningarna som numera också heter drop-in. Det får väl sägas vara en fenomenal succé från början. Första gången som jag tror den här bilden är från kom det runt 60 personer. Det kan ha kommit ännu fler. Och sen kan man säga att varenda måndag, för det har vi numera det här halvåret öppet varje måndag för barn och barnfamiljer, men även alla andra intresserade att bara komma in. Och det roliga också, det är att den absoluta merparten som deltar i de här drop-inen är med, är på Tycho Brahe-observatoriet för första gången. Det är en massa premiärgäster. Och de bjuds på lite avslappnat samvaro. Vi brukar berätta lite grann, de av oss som är där, om ASTB, TBO. Sen visar vi upp vårt fantastiskt fina nya teleskop. Och därefter samlar vi ihop dem igen in i stora salen där ni ju sitter nu. Och så håller jag något litet föredrag. Och jag har ju en hög som jag har tagit, som jag samlar på mig, för jag håller ju också på att driva vår barnverksamhet på TBO. Men kanske mer om detta. En succé och väldigt roligt att det är så många som kommer nya på besök. Så byter vi kanske bild. Ja, här kommer den här bilden. Då blev det så där att det blev barnverksamheten. Jag och min fru Carina, vi leder de 2 yngsta grupperna. Vi har rymdungarna och sen har vi NASA-gruppen. Och på bilden här är då NASA-gruppen. Här gör jag ett tappert försök att göra ett gruppfoto, en gruppi. Men ja, de är i alla fall med, även om de är lite suddiga.
Men du blev ju bra.
Ja, jag är bra, vilket är det viktigaste.
Du
Eller
kom
hur?
med på ett hörn.
Ja, precis. Kul. Bra. Det här är NASA-gruppen som är då mellangruppen. De allra yngsta kallar vi för rymdungarna. Och rymdungarna är mellan 5 och 8 ungefär. Och sen är då NASA-gruppen mellan 8 och 12. Och det är väldigt flytande. Vi tar liksom hellre och går efter intresse och mognad. Så vi har ju en 7-åring med i NASA-gruppen. Men han passar perfekt. Sen förutom de här 2 grupperna så finns det ju ytterligare en grupp som då heter observatoriegänget eller obsgänget, och den leds av min kollega då Olle Frykstam med benäget bistånd av en av deltagarna som heter Emil Hultin. Och då måste jag ju bara få säga detta, och nu kommer det ju inspelat också. Emil började alltså för 10 år sedan i observatoriegänget för att han var intresserad då av astronomi. Och idag så läser han astronomi på Lunds universitet. Och det är ju lite häftigt. Han har själv sagt att naturvetenskap ville han läsa på universitetet, men astronomin, ja, det var nog att han deltog i ungdomsgruppen eller mellangruppen. Så det är ju kul. Så här ser vi en bild på dem. Så kan vi väl gå vidare. Och sen förutom all skola och allmänt öppet så deltar vi också i något som kallas för kul i Malmö. Kul i 5 kan det också heta när det gäller februarilovet. I år så var det så att deltagarna fick en föreläsning i vårt solsystem, och därefter så skulle de tillverka sin egen modell. Så vi hade, jag och Carina, vi hade liksom flörtkulor, vi hade pinnar och vi hade sågat till små träbitar där man kunde ställa dem på. Och då fick de antingen ta och göra en av våra planeter eller en i fantasin. Jag ska flytta mig själv lite här och se vilken det är. Det här är ju en bild på vår sol. Den är ju bara helt underbar. Och nästa bild tror jag också, ja, även detta är ju en helt fantastiskt vacker planet. Lite osäker om det är någon av våra eller om det är en fantasiplanet. Jag vet inte om det var en tredje bild från just det här tillfället. Jo, här har vi det. Här har vi samlat ihop några stycken. Ja, här ser man ju vad de heter. Det är ju Mars till vår vänster, Neptunus. Ja, någonting, och solen. Och så, ja, ytterligare en. Så det här var resultatet, och det här fick de ta med sig hem då, och vi får väl se om vi får några nya deltagare i rymdungarna NASA-gruppen, för det lockar vi ju alltid med. Sen vet jag inte om det var den sista bilden eller
Jo, det tror jag.
För då vill jag bara lägga till att jag idag alltså har, vi kan ju ta bort den här bilderna igen kanske.
Jag ska göra ett försök.
Kanske. Vi kan ju alltid hoppas att det funkar. Så kan jag bara avsluta med att säga att jag alltså har varit ute i verkligheten idag. Jag har varit i Bjöd på Rutsborgsskolan och haft en temadag astronomi. För det är ju en del av mitt arbete också. Jag tar emot besökare på observatoriet, har visningar. Och det visar vi naturligtvis också upp vårt teleskop, stora teleskop. Men det jag gjorde idag, det kallar vi för temadag astronomi. Och det innebär då som sagt att jag åker ut till skolor och så har jag en hel dag. 4 timmar höll vi på med dagens tema som var gravitation. Så det gjorde vi med ett antal olika experiment, undersökte den Bland annat så hade vi med hammare och fjädrar här hemifrån våra papegojor. Det är ett klassiskt experiment som Galilei från början funderade ut och som man kan se att en av astronauterna från USA gjorde när de var på månen.
Det var ingen som fick ett äpple i huvudet eller så?
Inga äpplen i huvudet, inga glaskulor heller eller andra hårda saker. Så det höll vi på och jag antar att, eller jag upplevde att både barnen och lärarna var nöjda. Och sen var vi väl lika trötta allihopa efter detta intensiva men otroligt roliga aktivitet. Så, det var vad jag skulle berätta om.
Du får en applåd där.
Tack. Tack så mycket.
Ja, då ska vi gå vidare i vårt lilla program och då är det ingen mindre än Ronny här som ska berätta om våra senaste snygga astrobilder.
Ja, då har jag fått äran att visa lite av nya bilder som är tagna ut av mig och Max Ullberg, en annan av våra medlemmar och astrofotografer här i sällskapet. Tyvärr så tanken var att Max skulle vara med här idag och själv prata om de två första bilderna, men har tyvärr inte haft möjlighet att dyka upp. Så att jag har inte så supermycket bakgrundsdata kring de här två bilderna, men jag tycker de är så fina att vi ändå ska se på dem. De har han tagit nu här i vintras, de senaste januari, februari här, och vad vi ser på bilden här känner nu de flesta av er igen. Det här är Messier-objektet nummer 45, M45 eller Plejaderna som de också kallas. Eller Sjusystrarna som också är ett av de namnen som de går under. Namnet Sjusystrarna kommer ju utav att med blotta ögat så kan man under okej förhållande ana att det är 7 stycken stjärnor som är lite starkare. Och har man riktigt bra förhållande så påstås att man kan se 14 stycken stjärnor i den här öppna stjärnhopen som det här är. I själva verket så är det drygt 1000 stjärnor som den här öppna stjärnhopen består av. Det som är vackrast i den här bilden tycker jag är själva den blåa nebulositeten. Och vad vi ser i denna bilden, det är så kallad reflektionsnebulosa. Det innebär att det här är gas- och stoftmoln som lyses upp av stjärnorna och stjärnornas ljus reflekteras i nebulositeten. Därav namnet då reflektionsnebulosa. Nu så han har tagit en ganska så vidvinklig bild så han har fått med även här borta ni ser detta område som inte har det här samma blåa skenet utan mer ett brunaktigt sken istället. Den är inte alltid man ser det på bilderna så det tyckte jag var väldigt lyckosamt att han har fått med här.
Fråga.
Absolut.
Nebulositeten ser ganska strimmig ut. Är den så eller är det bilden som blir?
Det ser ut så här. Bra fråga. Jag vågar faktiskt inte riktigt svara på varifrån själva den här strimmigheten kommer. Men en rolig detalj som jag kan berätta om det här är att de här stjärnorna har egentligen inte med själva nebulositeten att göra utan de här stjärnorna är på väg. Alltså allting i rymden rör sig, stjärnor förflyttar sig. Och den här stjärnhopen är då inte skapad ur det här gasmolnet utan det råkar bara just nu vara väl placerat för att lysa upp det här och skapa det här fantastiska motivet för oss.
Är alltså de stjärnorna, är de så att säga hitom eller bortom?
De är i stoftgasmolnet nu, men det är inte där de är skapade. Utan de bara råkar vara där nu lämpligt nog för oss. Vi tar nästa bild. Det här är motivet. Efter något så vackert som LDN 935. Kallas också mexikanska gulfen. Troligtvis vad jag vet så är det väl på grund av, ni får rätta mig om jag har fel, men att det påminner om ifall man ser på en karta över mexikanska gulfen så ska det här på något sätt vara liknande detta. Jag har inte supermycket data här kring bilden heller hur Max har tagit den, men jag tror att han har tagit den med en monokamera, det vill säga en kamera som egentligen fotograferar svartvitt. Men att han sedan har fotograferat genom olika filter för att få fram de här färgerna. Jag är kanske lite ute på halis, men jag tror att han har betett sig på detta sättet när han tog den här bilden. Då så ska vi faktiskt kika på något annat. Det här är inte en bild som jag har tagit. Det är en bild som ska visa det området där vi hittar mitt nästa objekt som är en bild jag har tagit. Och om vi tittar här uppe så har vi skärmbilden kusken, Auriga. Den hittar ni genom att de flesta av er kan säkert hitta Orion, och följer man Orion och hans huvud högre upp så hittar man en väldigt ljusstark stjärna, Capella, som är den tredje ljusstarkaste stjärnan på vår stjärnhimmel, om jag minns rätt. Tittar vi lite närmare på själva Auriga så kan vi se en del saker markerade här. Och det var det här området som jag var lite nyfiken på att fotografera. Och då gjorde jag det i januari. Och som ni vet så var januari det var inte mycket stjärnklara nätter. Det har inte detta året överhuvudtaget varit. Men jag lyckades faktiskt under 5 nätter samla ihop totalt 16 timmars data. Och lyckades då få fram den här. Den här bilden består av ett antal olika nebulosor som jag tänkte berätta lite grann om. Här nere, den som mest dominerar bilden, det kallas The Flaming Star Nebula. Och är då ett stoft gasmoln som lyses upp av i huvudsak. Det finns en väldigt ljusstark stjärna här. Den ter sig inte så ljusstark kanske för oss, men där den är så är den otroligt kraftig, den här stjärnan. Och den då lyser upp det här stoftmolnet och skapar både en reflektionsnebulosa, det som jag pratade om innan, att stjärnans ljus reflekteras, men också emissionsnebulositet. Och det innebär att stjärnans strålning gör att gasmolnet börjar släppa ifrån eget ljus ifrån sig. Och då får man det här röda färgerna oftast. Lite högre upp här så har vi en annan nebulosa som heter, om jag skulle översätta den så, grodyngelsnebulosan. Jag vet inte för jag ska se om jag kan zooma. Nej, det kunde jag inte. Kan jag göra någonting för att zooma här? Nej. Okej. Okej. Och på den här bilden, ni kan kanske inte se det, men här finns 2 stycken små objekt som om man zoomar in på dem så ser de faktiskt ut som 2 stycken små grodyngel. Och det är områden där det pågår lite stjärnbildning. Och i hela det här området så finns det en öppen stjärnhop också som hjälper till att lysa upp den här nebulosan så att den får sig det här, som i min bild, blåröda skenet. Ytterligare en liten detalj som vi kan hitta i den här bilden, det är området här uppe. Här kan ni också se en öppen stjärnhop, och det är faktiskt ännu ett av de här Messier-objekten. Messier 38, en öppen stjärnhop som gömmer så här. Vill man sen så kan man gräva sig vidare och hitta. Det syns lite dåligt, men här finns ytterligare en öppen stjärnhop, och i de här 2 ljusa områden så är det också stjärnhopar som ligger och lyser upp nebulositeten. De här olika nebulosaområdena kan jag säga att de ser ut, när vi tittar på den här bilden, som att de ligger i närheten av varandra. Men den nedre, Flaming Star nebulosan, den är på ungefär 1500 ljusår ifrån oss. Så ljuset som vi tittar här, liksom åkte iväg för 1500 år sedan. Medan den här nebulositeten faktiskt befinner sig mer än 12 000 ljusår bort. Så avsevärt mycket längre bort, men vi kan ju inte bedöma de avstånden så här i en bild, utan här ser det ut som att de ligger i närheten av varandra. Men när vi då vet det så kan vi också sluta oss till att den här nebulosan är otroligt mycket större. Den är faktiskt nästan 100 ljusår i diameter över denna, så att det är otroligt stora strukturer som vi tittar på i den här. Sista jag väl kan säga om den här är att det här nebulositeten som jag tycker man kan se olika saker i det. Jag vet faktiskt inte vilket det tillhör, eller det tillhör det bortre eller det främre eller ifall det är faktiskt ett helt fristående nebulositet. Jag har inte lyckats få fram det när jag har läst på om det här.
Här har du väl lite tekniska data, antar jag?
Jag har det. Man kan rabbla på här hur detta är taget. Som sagt var, jag har tagit med faktiskt med väldigt litet teleskop, inte i närheten av något sånt här monster som vi har här ute, utan ett litet teleskop som egentligen ser ut som en teleobjektiv till en kamera. Och så som sagt var har jag då, precis som jag berättade om Max, har jag fotograferat med en kamera som bara registrerar svartvitt och fotograferat genom olika typer av filter som man sen sätter ihop och då får man det här resultatet.
Det är 1000 sekund.
Här är ju som sagt var det är ungefär 16 timmars exponering i den här bilden så det har blivit en del bilder. Just det här har jag lagt på lite information. Egentligen det jag vill säga med det här att ni ser här gradangivelserna. Här ska vi tänka på att månen upptar ungefär 1/2 grad ifall vi tittar på den upp på stjärnhimlen. Och ni kan se här har vi 4 grader från vänster till höger. Det vill säga det här är ett stort område av stjärnhimlen som vi tittar på. Så att här hade vi fått plats med 8 stycken fullmånar från vänster till höger. Så att det är ett stort område som det här upptar på himlen. Sista som har med den här bilden att göra, det var att jag ville visa att som ett steg i bildbehandlingen men också ett sätt att faktiskt titta på nebulositeten så brukar jag göra så här att jag plockar bort stjärnorna. Det finns funktioner i en del program man kan göra det. Och det som jag tycker är spännande med det är att plötsligt så framträder nebulositeten ännu mer när man kikar på den. Man ser detaljer som man kanske inte ser när stjärnorna är där, för att stjärnorna de distraherar lite grann. Men plötsligt ser man väldigt mycket mer när man tittar på en sån här bild. Så jag tycker det är ett ganska så skojigt sätt att...
Och det är isolationer du har på.
Vad sa du?
Isolationer eller kanalhjärnor som du observerade på en.
Det är observerat utifrån, strax utanför Staffanstorp. Där nu går jag och där sätter jag ut mina grejer på nätterna. Så att detta är någonting som man kan göra härifrån. Vi har folk inne i Malmö som bor med ännu mer ljusföroreningar än vad jag gör utanför Staffanstorp och som tar minst lika bra bilder. Det handlar bara om tålamod och att man samlar mycket data under många nätter och då kan man få fram sånt här.
Så det räcker inte att man skulle stirra på det här stället 16 timmar?
Nej, våra ögon är lite för primitiva för det. Utan, då får vi utveckla våra ögon först lite grann till. Jag har en bild till som jag tänkte visa er som inte har med denna nebulosan att göra. För vi går ju mot ljusare tider så det tyckte jag det var läge att ta en liten titt på vad som händer på solen. Så att i förrgår så plockade jag fram mitt solteleskop där hemma och tog den här bilden. Och lite av anledningen till att jag vill göra det är att jag vill uppmuntra er till att ifall ni har möjlighet att kika på solen nu för att vi närmar oss ett tillfälle där det är väldigt mycket aktivitet som pågår på solen. Just nu så kan vi se här till exempel en stor solfläck som vi har mitt framme på solen. Och vi ser att det är mycket som händer här i randen runt omkring. Man kan se en del mindre utkastningar. Det var ingenting stort på gång den här dagen när jag hade framme mina grejer. Men som sagt var, det är mycket aktivitet på solen just nu och det kan nog komma till att bli ännu mer också under det närmaste året som vi har framför oss här. Mer har det inte blivit i år. Det har varit som sagt var, det har inte varit astrofotografernas tillfälle riktigt än utan det har varit mörka nätter men tyvärr fullständigt molniga. Så
det blir mycket bättre än det här.
Vi hoppas på att det ska börja produceras lite mer nu ifall månaden skulle vilja försvinna. Ja.
Innan du kom in på Grodingen-nebulosan så pratade de om att stjärnorna omkring strålar så mycket så att det lyser av sig själv. Menar du att de värmer upp gas?
Nej, vad som händer är att... Nej, om du tänker dig som neonljus. Vad som händer är att strålning, det är väldigt intensiv strålning från solen som... Vad säger nu? Den skickar väl in elektroner i atomerna. Hoppas jag inte det är tvärtom.
Alltså,
Och sen när atomerna släpper ifrån sig de här extra elektronerna, då släpper de också ifrån sig ljus.
alltså nebuloserna exciteras ju utav framförallt UV-strålning då från heta stjärnor som nybildade stjärnor är oftast heta.
Ja.
Så det hänger ihop lite så. Men då i med
Att, dels det och den rena reflektionen också som blir.
Ja.
Så det var vad jag önskar vi hade haft mer att bjuda på, men det är vad året har gett än så länge.
Det var helt utomordentligt trevligt att se. Så tack så jättemycket. Ja, jag tänkte göra en liten ändring i programmet faktiskt. Jag pratade med Mirja nyss. Och våra duktiga gymnasister. Jag ser nu att jag har Vilma här inom räckhåll och Jasmin har jag sett tidigare. Ni ska ju berätta om ert gymnasieprojekt som ni gjort här ute. Är ni redo för att göra det?
Yes.
Vad bra. Det var Jasmin som sa det, gissar jag.
Precis.
Ska vi se om vi kan få in er lite i bild också. Det vill vi ju hemskt gärna ha. Jasmin, där är du i alla fall. Jag fäster dig här på skärmen som man säger. Välkommen. Och välkommen också då Vilma naturligtvis. Ni är på olika ställen förstår jag. Berätta lite. Och berätta om er själva och berätta naturligtvis om hur tusan ni lyckades bestämma Hubble-konstanten från observatorium. Varsågoda.
Ja, vi kan ju börja med att presentera oss då. Och sen har vi en presentation och hur det ser. Och mitt namn är då Jasmin. Jag går på amerikanska gymnasiet, Stora Essingen här i Stockholm. Och läser då naturprogrammet.
Och?
Yes, och jag heter Vilma och går också på gymnasiet i Stockholm på naturprogrammet. Men jag går på Viktor Rydberg.
Välkommen du också. Bra.
Tackar.
Ni har ordet. Varsågoda.
Ska vi se om jag kan delas skärm.
Ja, det ska kunna gå.
Så. Ja, vi har då skrivit ett gymnasiearbete om Hubbleslag och konstant. Så när vi fick uppdrag nu i årskurs 3 att göra ett gymnasiearbete blev vi båda väldigt sugna på att hitta ett ämne kopplat till astronomi. Vi fastnade snabbt för galaxer och bestämde oss i princip för att göra en litteraturstudie på galaxers evolutioner. Men hur som helst bestämde vi oss även för att kontakta er på Tycho Brahe-observatoriet för att se om det fanns en möjlighet för ett samarbete. Och det visade sig att ni kunde erbjuda en observation och viss handledning. Vi var dock fortfarande väldigt sugna på att just forska om galaxer och bestämde oss därför för att komma upp med en egen idé istället för att utgå från era projekt som ni erbjuder. Efter lite bollning av idéer och några möten slutade det med att vi skulle studera avlägsna galaxer där vi skulle bestämma deras rödförskjutning och hastighet för att verifiera Hubbles lag. Problemet var att vi inte riktigt visste hur det skulle gå till. Vi hade inte tillgång till den utrustning som krävdes för att genomföra detta, men vi tänkte att det på något sätt skulle gå. Om inte annat ville vi att det skulle gå. Det skulle ju vara kul att få använda ett teleskop när vi hade möjlighet. Med fulla krafter sökte vi runt för att hitta ett lämpligt tillvägagångssätt. Men hur mycket vi än vände upp och ner på formler slutade det i en spektroskopi som inte var möjlig. Men ett par veckor senare, efter många timmar, dök en bekant formel för kosmisk distans upp på Wikipedia av vad som liknade parallaxmetoden, men där mätningarna inte behövde göras över tid som vi inte hade. Hur som helst visste vi att i och med att mätningarna blev simplare skulle det även medföra större felmarginaler i beräkningarna. Och syftet med arbetet blev då att observera avlägsna galaxer och analysera deras rödförskjutning, varvid den framtagna datan kunde användas för att bestämma galaxernas avstånd från jorden samt deras respektive hastighet, och på så sätt verifiera Hubbles lag. Genom att sedan tillämpa denna kunde vi bestämma Hubbles konstant och universums ålder med tillhörande felmarginaler. Detta sammanfattade vi med en frågeställning av hur påverkar den skenbara diametern hos avlägsna galaxer noggrannheten och tillförlitligheten i bestämningen av deras avstånd? Och hur kan tillämpningen av den erhållna datan användas för att verifiera Hubbles lag och därmed estimera Hubbles konstant och universums ålder med tillhörande felmarginaler?
Yes, så vi tänkte börja med lite bakgrund. Så 1929 så publicerade Edwin Hubble teorin om att universum expanderar, vilket visade på ett häpnadsväckande enormt universum som har expanderat och förändrats i ungefär 14 miljarder år. Hubbles lag är en nyckelparameter inom kosmologin och bygger på idén att avlägsna galaxer rör sig bort ifrån oss och att deras fjärmande hastighet ökar proportionerligt mot avståndet. Och på sliden här nu så ser ni den ursprungliga Hubble-grafen som publicerades tillsammans med teorin 1929. Och det här linjära sambandet som bildas visar på att universum expanderar kontinuerligt och enhetligt i alla riktningar. Lutningen på funktionen är känd som Hubbles konstant och det svarar mot hastigheten för vilken universum expanderar med. Om man säger att hastigheten varierar över tid, alltså att galaxer på ett större avstånd ifrån oss har en högre fjärmande hastighet. Och det här säger man då trots att konstanten är konstant i alla riktningar i alla givna tidpunkter. Formeln som Hubble kom fram till är den här som kommer upp här. Och en galax fjärmande hastighet kan då definieras som Hubbles konstant, vilket är då det här h med index 0, multiplicerat med avståndet från oss på jorden, och det är då det här d1. Och enheten är kilometer per sekund per megaparsec. Konstanten kan även uttryckas som en funktion av tid, och det kallas då för Hubble-parametern. Och idag betecknas just det här värdet h med index 0 och svarar då mot Hubbles konstant. Och det erkända värdet som vi idag vet om ligger på ungefär 70 kilometer per sekund per megaparsec. Och tar man inversfunktionen av Hubbles konstant, som vi tar 1 genom h0, så svarar det mot Hubble-tiden, och det är då den här tiden sedan Big Bang. Och tar vi 1 genom 70 så får vi ett universum är ungefär 14 miljarder år.
Och teorin bygger på mätning av rödförskjutning varvid galaxens emitterade elektromagnetiska strålning förlängs under resan till jorden, som konsekvens av att strålningskällan rör sig bort relativt oss. Vad Hubble konstaterade var att i universums expansion att det är den som orsakar utdragning av ljusets våglängd, där volymerna av rumtid är vad som expanderar. Och idén om vad som sker ser ni här på bilden. Fenomenet betecknas Z och definieras så här enligt formeln till vänster. Där lambda är den observerade våglängden och där lambda med index 0 är den emitterade våglängden som galaxen sände ut för ett antal miljarder år sedan. Detta är då formeln som vi har utgått ifrån, och sen har vi själva härlett den här formeln till vänster för galaxens avstånd genom trigonometri, där alfa står för galaxens vinkeldiameter, alltså den diameter som vi mäter från jorden i teleskop, stora D för dess faktiska uppmätta diameter och lilla D för distansen mellan galaxen och oss.
Yes, så det vi har gjort är sedan att observera de här 4 galaxerna som vi har skrivit upp här. Och sen har vi då tagit ett foto av dem. Just de här bilderna är dock lite manipulerade i planetarieprogrammet Astro Imagery för att framhäva kontrasterna bättre. I samma program så använder vi sedan deras mätverktyg för att bestämma hur många pixlar respektive galax tog upp. Och upplösningen blev inte jättebra och därför fick vi väldigt stora mätosäkerheter. Men givet från användarmanualen som vi fick från er på observatoriet så har vi sedan kunnat översätta pixlarna till bågsekunder, vilket i sin tur kan omvandlas till grader, och det är då det måttet vi behöver för att beräkna deras vinkeldiameter och då även distansen. Den faktiska diametern och rötförskjutningen sökte vi sedan upp astronomiska arkiv, och när vi sedan gjorde alla beräkningar för allting så fick vi fram de här resultaten som är redovisade i ett Hubble-diagram där vi har då distans på x-axeln och hastighet på y-axeln. Och de individuella resultaten för varje galax har vi markerat med små kryss. Och sen genom linjäranpassning så kunde vi då ta fram lutningen, vilket svarar mot Hubbles konstant. Och det är då den lila mittersta linjen. Den gröna och blåa funktionen representerar felgränserna utifrån en beräknad felkalkyl. Så det är alltså det maximala och det minimala värdet som konstanten skulle kunna anta med hänsyn till mätosäkerheten. Och värdena vi fick fram kunde vi sedan avrunda till 39, och felmarginalen fick vi ungefär till plus minus 100 kilometer per sekund per megaparsec. Och för universums ålder så fick vi fram det genom att beräkna Hubble-tiden, och då fick vi ett värde på 26 plus minus 70 miljarder år.
Med de presenterade resultaten kan vi verifiera Hubbles lag, men däremot så utgör mätosäkerheten i observationerna en viktig aspekt för att säkerställa precisionen i resultaten. De beräknade värdena kan därmed varken bekräfta Hubbles konstant eller universums ålder. Anledningen till att resultaten avviker så pass mycket som det gör är troligtvis för att metoden är väldigt osäker och inte exakt nog för att minimera felmarginaler. De låga upplösningarna i galaxbilderna ledde bland annat till att vi inte med säkerhet kunde urskilja galaxernas begränsningar. Här är ett exempel på bilden där det är väldigt svårt att avgöra vad som faktiskt tillhör galaxen och vad som är utomstående brus. Vad som mer skulle kunna leda till felaktiga resultat är att endast ett begränsat urval av mätvärdena användes, då vi endast hade tid att observera 4 galaxer. Det finns då en risk för slumpmässiga variationer där minsta avvikelse kan bidra till stora felmarginaler.
Så även om de båda erkända värdena faller inom våra beräknade felgränser så är de så pass stora att de innefattar negativa värden. Och en negativ konstant, alltså Hubbles konstant, skulle innebära en sammandragning av universum snarare än expansion. Och en negativ ålder är inte rimlig. Så vi ser då vilken betydelse noggrannheten i mätmetoderna har på resultaten och kan därmed dra slutsatsen att metoden som vi har använt är ganska osäker och endast ger en indikation på att lagen stämmer, samt att den i ett övergripande syfte endast är precis nog att uppskatta Hubbles konstant och universums ålder. Vi kan slutligen med säkerhet säga att en observation kräver ytterligare utforskning på metod och noggrannhet i observationer för att mer exakt fastställa värdena och således säkerställa deras överensstämmelse med etablerade vetenskapliga normer. Hur som helst så ger resultaten en grund för fortsatt analys och diskussion kring Hubbles lag och deras relevans för vår förståelse av universums expansion. Yes.
Ja. Vi är förstummade allihopa, tror jag. En applåd för oss. Vi blir alltid förstummade nästan när gymnasister redovisar sina observationer och sina projekt utförda här med vårt fjärrstyrbara teleskop. Och när ni kom med det här förslaget, jag har ju då hjälpt till med handledningen, så var det väl ganska uppenbart, eller svårt att tro att det skulle här verkligen kunna göras överhuvudtaget. Men det har ni ju gjort. Alltså ena hälften har ni gjort, kan man säga. Ni kanske kan kommentera det lite med hastigheten lite mer. Hur fick ni fram de här hastigheterna som ni använder av för galaxerna?
Vi sökte upp rödförskjutningen i ett astronomiskt arkiv och sen så tog vi då rödförskjutningen för varje galax och så gångrade vi det med ljusets hastighet.
Mm. Så att just det, rödförskjutningsdata det tog ni från arkiv helt enkelt då, ja. Ja. Vi kan ju inte göra spektroskopiska mätningar här ute på det viset. Att när ni nu gjorde det här försöket så ska ni väl ändå vara rätt övertygade om att ni inte är de enda genom historien som har försökt att bestämma Hubble-konstanten. Utan det är ju verkligen lite av den heliga graalen på lite, kan man säga. Att inom astronomin att kunna fastställa den med så hög noggrannhet som möjligt. Så det har ju gjorts oerhört många professionella djupsinniga projekt för att göra detta. Och ni är ju då på vägen här, va? Ni tillhör ju ett ganska exklusivt gäng, kan man väl ändå säga. Det är ju fortfarande i viss mån omtvistat faktiskt det verkliga värdet på Hubble. För det finns resultat från olika typer av mycket avancerade observationer som fortfarande inte helt och hållet överensstämmer, så vitt jag vet i varje fall. Och James Webb-teleskopet är ju bland annat också involverat i sådana här observationer. Och då, James Webb får vi ändå erkänna är något bättre än vårt teleskop här ute. Lite grann i alla fall. Men jättetrevligt. Någon fråga härifrån publiken, vare sig den är virtuell eller verklig? Nej. Jag kan väl utgå från att era lärare kommer att bli ganska imponerade. Har ni presenterat detta redan eller hur ser det ut?
Ja. Eller jag har i alla fall. Jag tror inte Jasmine har gjort det än.
Just det, ni gör det vid olika skolor vid olika tidpunkter, förstår jag.
Mm.
Okej. Fick du någon reaktion då när du lämnade in det till godkännande så att säga? Vilma?
Alltså jag har fått godkänt. Så mycket har jag ju fått. Men inget så mycket mer än så.
Okej. Ja, nej. Ja, alla lärare är inte lika välutbildade kosmologer kanske. Hur som helst, tack så jättemycket. Det var hemskt trevligt att höra. Jag hoppas att ni tycker det var trevligt att göra de här sakerna också här ute. Så att då tackar vi er och då är det Mirja som är vår nästa lilla föredragshållare eller vad vi nu ska kalla det för. Du ska ju helt enkelt berätta det senaste rymdnytt. Och då ska vi se om jag kan trolla fram det också.
Ja.
Vi gör ett försök. Så då. Varsågod.
Okej, tack så mycket. Jag fick det här uppdraget sådär hastigt och lustigt. Och precis i dagarna då var det ju massa nyheter om en ny raketuppskjutning till månen. Jag plockade fram sen lite grejer, bland annat forskning och framsteg hade uppmärksammat detta. Att det är många som har försökt. Vilka som har lyckats så vet jag inte. Jag ska bara försöka flytta mig här. 22, så där kom den här Artemis 1.
Du får prata lite högre.
Som testade då om det skulle kunna flyga och den gjorde faktiskt en rundresa vid månen. Och det var NASAs det här stora projektet som de skulle så småningom kunna fixa människor igen på månytan. Men där var också Dainuri, som det är en kretsare från Sydkorea. Och den pågår fortfarande. USA har också skickat ut Capstone och jag vet inte om det här är en privat grej eller om det för att det stod inte riktigt uppgifter om det. 2023 Chandrayaan, den här trean som Indien som har varit väldigt framgångsrik med sina landare och strövare dessutom, skickade upp en tredje sån och den funkade i 10 dagar. Men den här kretsaren funkar fortfarande. Luna var en rysk landningsförsök och den bara kraschade. Även Rashid som var Förenade Arabemiratet, det var också en misslyckad sådan. Och då har vi kommit ända upp till detta år. Och då fick jag faktiskt idag finska Tähdet och Avaruus. Och de har också uppmärksammat detta med en massa månförsök. Och bland annat har de skrivit om detta, den här Slim och Peregrin landare. Den här japanska landaren, den lyckades ju. Men det här Peregrin som det står att det misslyckades, men det var inte liksom... Det var mer i detta än bara den här Slim japanska grejen, så den föll också omkull. Alltså på sidan, den släppte en liten mini kravlade upp på den här månytan. Okej, då är vi uppe på den här senaste som var uppskjutet den 15 februari och landningsförsöket var alltså nu den vad har jag skrivit? Har jag skrivit den här? Nej, det var Den skulle landa den 22. I alla fall, jag höll på att titta en del av den här. De miste plötsligt, alla grejer sa att den hade landat. Och sen plötsligt tappades kontakten. Och de jobbade frenetiskt med detta. För att det var en massa saker som hände. Som antagligen orsakade just något fel på landningen. Och det är inte så himla lätt att nå månen. Det är många som har försökt. Så jag fortfarande begriper inte hur de egentligen fick NASA, att de fick de här 17 astronauter som har gått på månytan dit med datorer som hade mindre kraft än en vanlig sån här mobiltelefon. När de nu varannan kraschar i stort sett, försöker bara sätta en landare dit. Det finns en väldigt bra YouTube-kanal som heter Scott Manley, som är amerikan. Och han har en väldigt bra kort sammanfattning av just den här och allt vad som hade gått, allt som gick lite fel. Slutsatsen var liksom då att de kunde konstatera att den hade tippat. Den hade helt enkelt fallit på sidan. Men den fortfarande klarar av att skicka data. Den har ju bara planerat att kunna fungera tills månnatten helt enkelt. Det är bara några dagar till faktiskt som det kan fungera. Den ligger ju nära Sydpolen dessutom. Det som var ganska intressant med den här första kommersiella företagslandningen, så de har skickat utöver vetenskapslast dit. NASA hade 6 stycken sådana här vetenskapliga uppdrag. Men bland annat hade de en konstverk av Jeff Koons som föreställer månens olika faser. Och sen var det ett jätteprojekt av musikern Santana som har skickat dit en arkivutdrag. Santana har faktiskt varit grundare för en sån här jättearkiv, digital arkiv av konst och konst i musik och konst. Att de har alltså digitaliserat till och med sumerisk kilskrift och allt möjligt sånt. Men just att de har väldigt mycket amerikansk musik. Så där var bland annat då i den här titanplattan grejer bevarade från Elvis och en massa andra. Luna Prize hette den. Marvin Gaye, Santana, Jimi Hendrix, Chuck Berry, Bob Marley, Janis Joplin och tagningar från Woodstockfestivalen 69. Och dessutom en sån här dokumentärfilm av Michael P. Nash som heter Climate Refugees från 2010. Och den är ju fortfarande väldigt aktuell. Och det finns en trailer för den här filmen som man kan se. Den har vunnit jättemycket priser. Och den här Nash, han planerar nu en fortsättning med arbetsnamnet Chasing Truth. Med bland annat Leonardo DiCaprio, som kastar lite sådana fina namn här. Där var också ytterligare andra konstverk, bland annat den här är gjord av den här Nash. Där är då bilder, konstverk som är lagda liksom ungefär på ytan av månen. Den var ganska fin. Och det finns väldigt mycket nytt som händer annars. Och det sista var faktiskt en liten kortis. Ni vet ju den här lilla helikopter Ingenuity. Den har dött. Så jag blev så ledsen när jag läste om det. Men den översteg ju funktionstiden väldigt kraftigt.
Miriam, stort tack för och därmed har vi kommit till halvtid som ni inser. Och därmed är det ju Kalle där som blir huvudmannen. Som ju fixar med självkostnadspris kaffe och kakor. Och teleskopet nu, vårt nya fina teleskop, är alltså öppnat. Och det går bra att titta där ute på djupet. Så att välj det ena eller det andra, men försök att jämna ut det lite så att inte alla är på ett ställe samtidigt. Så ses vi igen om en kvart, 20 minuter ungefär. Okej, var snälla och hitta era platser igen här. Välkomna tillbaka. We have sound and we have video and everything set up. Vi är framme då vid kvällens höjdpunkt, föredraget förstås. Och det handlar ju om extrema exoplaneter. Och då har vi också tagit hit en extremt duktig astronom. Han heter Jens Hoeijmakers.
Very good. That's perfect. Her words.
I did ask him before, yes, to see if I can manage that. So very much welcome, Jens, which is easier to say.
Yeah.
Jens is working as a senior researcher at the Lunds observatory, as we prefer to still call it, by the way. And he is doing research on what some of us would call hot Jupiters. That means, of course, exoplanets close to stars. And the thing is that today you don't only discover the exoplanets. Today you study them. And you can study them in some detail, and that is exactly what you are doing. So very much welcome, and the floor is yours.
Yeah, thank you. Thank you very much, Peter. Thank you for the invitation as well. There you go. Thank you for the invitation. So my name is indeed Jens Hoeijmakers. I'm originally from the Netherlands. That's where the name comes from. My title is the Exoplanet Revolution, because I think we can really speak of a revolution in terms of what's happened on the exoplanet side of astrophysics. The first exoplanet has been discovered approximately a bit more than 25 years ago now, almost 30 years ago. And now about 1/3 of all astrophysics activity is exoplanets. So it is a very big field and it's growing a lot. I was asked to give a 45-minute talk. I'm hoping that I will stay within 45 minutes. It's fine if you want to ask me questions during the talk. I'm perfectly fine with that, but then the risk is that we're going to go a bit longer. So you can judge for yourself what you want to do. I was going to talk about extreme planets. I study and observe and study extreme planets. The downside of exoplanet science compared to a lot of other astrophysics is that we don't make a lot of pretty pictures. So we study a lot of data, and it's very small signals and data, and I'm going to show you some of that. But with that data, we can observe atmospheres of these planets despite the fact that they're very far away, we can observe their atmosphere, and we can learn very interesting things about these planets. And that's what I'm going to talk a bit about. And finally, I will say a few things about life, life outside of the solar system, or the potential for life on these planets. Of course, we don't know about this life just yet, so there's not that much to say, but there are some things to say, and I will share my opinion about life on other planets as well. Okay, so first a little bit about myself. I'm originally from the Netherlands. I've done my studies, all of my preparatory studies in the Netherlands. Until 2017, I was there, and then I moved to Switzerland for a few years, where I was working at the universities of Bern and Geneva. I spent 3 years studying exoplanets there. Geneva Observatory is a place where they build very advanced spectrographs that we use to observe exoplanets. And so I really went to the heart of the lion's den, basically, when it comes to exoplanets. Geneva Observatory is also the place where the first exoplanet was actually discovered. So this is really one of these places in the world where they kind of set the field in going, basically. And then in 2020, I moved to Lund University, or Lund Observatory, where I'm still working, and I hope to work for a long time, where I'm starting up my own group. I have a few students, and they are doing this research together with me now. All right, so in this talk, oh, that's the wrong, I've got 3 computers here in front of me. This is the one. My talk is going to be a little bit about how this whole field came to be and how it works. How do we find planets? What are the type of planets that we're finding? How do these planets even form? Because we're going to find that a lot of these planets are very strange compared to the planets that we have in the solar system. Finally, how do I, or we as a community, but I also, how do we study them? And finally, is there already something that we can say about habitability, habitable planets, and potentially even life? And for life, of course, we can look outwards, but it's still very early to say anything, but we can look back and we can look at Earth and already actually say quite meaningful things about life just by looking at the Earth. And that's what I will do at the end. Okay. So I'm going to show a beautiful picture as well. This is one of the only beautiful pictures I have of the night sky from somewhere on Earth. And of course, this is the type of picture that you're very familiar with and that people have been familiar with for thousands of years. Now, what is new since the last 25, 30 years or so, maybe not that new anymore, but still quite new, is that most of the stars that are in this picture have planets orbiting around them. We don't know for sure any particular star does. For example, I'm pointing at a star over there. Maybe it has a planet or not. But on average, every star on this picture will have a planet around them. In fact, more than one planet, probably multiple. And so this is really what the exoplanet revolution is about. We've gained the ability to say that and to discover that. Now, if you take a telescope, of course, you will find that there is a lot of stars out there. The galaxy has many billions of stars, and we now know the statistics. That is that every star has planets. In fact, we believe that every star might have a planet that is like the Earth, on average, at least. And so that is very exciting. When you think about extraterrestrial life, that is very exciting because we might imagine that life occurs on planets. And so it helps if there's many planets out there that we can maybe try to search for that. Okay, that's easier said than done. In fact, it's very difficult, first of all, to even discover these planets. That's why it took until 1995 to do so. We've been studying stars, even in quite a lot of detail for many decades. Even for 100 years, I can say that we've really studied stars in a scientific way. Exoplanets has been a lot later, and that's because it's very difficult to observe them. Imagine that you have a single star somewhere in that image. You might ask yourself the question, does this star have planets around it? And this answer is very difficult to obtain with anything but very advanced instruments. You need advanced instruments to do that. And the reason for this is that our star is a very bright light source, but the planet that is right next to it is not very luminous. It does not emit light of itself, almost not light by itself. Most of the light that it emits will be reflected by the star. And because the planet is very small and the star is very big, this is a very big contrast difference. You will see this compared with trying to find little flies circling around light posts, which there are often, but then at distances of very many kilometers. So it's very difficult to see these very small lights next to very bright lights. It's not the problem so much that planets don't emit light, it's rather that they are very next to very big lights, and so it's very difficult to discern them from the stars around which they're orbiting. The main reason for this, you might wonder, why can't I just take a very big telescope and zoom in, right? We do that. We do that all the time. We do that for galaxies. We can find galaxies that are many megaparsecs away, say all sorts of interesting things about the universe that I don't know much about. Why can't we just take a telescope and zoom in? And the reason is that there's a limit to how much you can suppress the starlight, and that is caused by diffraction. If I take any telescope, it will be able to resolve a star to a point source only that much, only that well. And the reason for that is the wave nature of light. Light behaves like a wave, and it creates these nice ripples when you image it. What you can do, and I could have actually done this experiment, if you had a laser pointer and you shine it through a pinhole in a piece of paper, you can do this at home. If you take a piece of paper and you take a needle and you puncture it, then shine a laser pointer through it, you get an image like that on the left-hand side. Because this hole has an interaction with the light that passes through it, it creates this nice wave pattern, and that is fundamental. That's a fundamental property of light. And telescopes do the same thing. So if I have a very big telescope, I can make a picture of a star like that, and it has this wavy diffraction pattern, that we call it, surrounding it. And within that diffraction pattern, your planets might hide. So if this is an image of an actual star, I'm going to use my cursor now, the orbit of Saturn might land somewhere in here. So all of the planets that might be there are very easily lost in the starlight. This is the fundamental problem that we have to solve. Now, you can make this problem better. You can address this problem by making bigger telescopes. That's what we do. But you will always have this effect happening and basically overpowering the faint light of our planets. Okay, this is generally the case for most. Yeah, that's nice. Maybe after the talk, we can actually do that. Someone brought a laser pointer. That's very good. You have to do it at a bit of distance and be close to the wall. So there's exceptions. There is a handful of cases where we can observe exoplanets directly, but those are very special cases. This is an example of one of those special cases. This is HR 8799. This is an exoplanet system where you can see the planet orbiting the star as you observe the system for years. So this is, you can see in the top right corner, the top left corner, the year of the observation. And these planets are orbiting their star. You can really beautifully see these orbits. The problem is that this is a very special kind of system, a system that is very young. When an exoplanet system is young, all the planets are hot and they emit their own light in the infrared, at infrared wavelengths. And that allows us to observe them directly. Most systems are not young. Most systems have average age. And then the planets are cold and then they don't emit. We have to look for their reflection, and that reflection is very weak. So this is the type of system that I think the first one of these was observed in 2009 or something thereabout. There's a handful of systems that we can study in detail by doing this, but most of the planets that we know about are not like this. Because of this contrast issue, we need to use indirect methods. And there's two methods that are mostly used. There's actually a dozen methods or so that you can use to find exoplanets, but there's two methods that are used mostly, until now at least. And that is the transit method and the radial velocity method. These do not use the light of the planet itself, but rather they use the effect that the planet has on its host star. So the star emits a little light, and the planet can have a little effect on that we can observe. The transit method is the most straightforward to understand. If you have a planet that orbits the star in the right angle, then the planet will pass in front of the star. And if you observe the brightness of the star, that will decrease when the planet goes in front of it. This is a normal eclipse. This will happen every time the planet goes around. So if you would observe the brightness of your star over a period of time, you can see that this effect repeats. And that allows you to observe that this planet orbits with a certain periodicity. This is fairly straightforward to actually do. You can do that with a small telescope. The telescope that you have over there is more than capable of using this method, and you should try it out once if you haven't already.
In fact, we have been doing that already.
We have been doing this. Very good. Very good. I think you can almost do it with a smartphone, actually, but the software inside the smartphone doesn't allow you to, otherwise you could. So this is fairly straightforward to do nowadays. You might wonder why it took until 1995 to do that, but I'll get back to that. The main problem with this method is that you need to have your orbit aligned such that it goes in front of the star. And for most planets, that will be not the case. All systems are oriented randomly in space. And so for a planet like the Earth, the probability that it would transit the sun, if you see it from any random direction, is about 0.1%. So even though most stars might have planets, most of them will not be seen to be transiting. That's the problem mainly with this method. The second technique requires spectroscopy in order to measure the effect of the planet. So in the spectroscopy, we'll take the light of the star and we will disperse it into all of its colors. Here's a nice image. I cannot escape from showing you this image, which is the spectrum of the sun. The sun spectrum has, from the blue to the red, has many spectral lines. All these black streaks are lines that are places, wavelengths, colors, where the light is absorbed because of some element in the sun's atmosphere. This is caused by various atoms, metals, that have very particular absorptions all over these wavelengths. And for example, here are the sodium lines. These are 2 lines created by sodium, which I sometimes study, and many other elements that are absorbing. Now, the point is that these lines allow you to measure velocities because these lines will shift due to the Doppler effect. This is the same technique that we saw just now when we were measuring velocities of galaxies. In order to determine that the universe expands, you can also measure the velocities of stars. And stars move in all sorts of directions with all sorts of velocities. The point is that when a planet orbits the star is tugged about due to the gravitational force of the planet. And that will move the spectrum of the star back and forth every time that the planet orbits. And so again, this is a periodic effect that you can measure if you can measure the spectrum of the star and derive from it the velocity. Now, this is a technique that depends on the mass of the planet. If the planet is more massive, it pulls more strongly, and so this is a measure of the planet's mass. The other technique, the transit method, blocks light, and so that is a measure of how large the planet is. So these two measurements together give you the radii, the diameters of your planet, and the masses of your planets as well, if you observe your planets in this way. Now, however, this method also has a problem, and that is that the velocity that the Earth would incur on the sun, would cause the sun to have, is about 9 centimeters per second. That's like this fast. So the entire sun is moving by a very small velocity due to the Earth's gravitational pull. And so if you are going to observe this, and we don't actually have spectrographs that can do this right now, but if you were to observe this, you need to be very stable. And you need to be stable over very long time periods, because it takes the Earth 1 year to go around the sun. So you need to have some sort of a spectrograph that's very stable over a year's times. That's very difficult to achieve. Yes, question?
You should have the other problem too. If the planet circles like that, you don't get any Doppler.
That's correct. This is also depending on how the orbit is inclined. And if it's not so well inclined, it also becomes a less strong effect.
But now, I mean, you have...
Please repeat the questions.
Yes, yes. Sorry, the first question was about that this is dependent on the inclination of the orbit. That is true.
You said, I suppose, as an example, Earth and Sun, if we look at that from
That's right.
But Jupiter is much more, it affects more. And I suppose in the most cases, there's plenty of planets, a couple of planets at least, and they will affect all of them dependent on...
That's right. So I use the Earth as an example. If you take, say, a planet of Jupiter, Jupiter has a larger effect. I think about a few meters per second. This we can observe these days. But Jupiter has the disadvantage that it's far away from the star, so its orbital periodicity is a lot longer too. So you still need high stability over a longer period of time.
So if you should look at the sun from another planet,
Yes.
what would affect most?
Jupiter.
Jupiter, Venus, Jupiter, or Mars?
Jupiter would do that.
It would.
Jupiter would be the biggest effect of the solar system.
But it's, of course, a very
But a long orbital period.
long period.
That's right. So this is the reason why detecting planets is very difficult, at least planets that are like the solar system planets. All right. This is also the reason, if you think back about this picture, why it has taken until 1995 in order to do these. These techniques are not very technologically difficult, or they're not theoretically difficult to understand. They're also not that difficult to implement. If you have telescopes, big telescopes and spectrographs, you can use these techniques. But the problem is that people were simply not really searching for planets until 1995. There's papers that detail these techniques from the 1960s, and they explain what you would need in order to find planets. And the answer is you can never do that. Even though they could, but they didn't, because it was thought to be a waste of time. Sometimes it goes like that.
And now 1/3 of all the research.
This is correct.
directed.
This is correct. So in 1995, the first planet was discovered around the star 51 Pegasi. It's called 51 Pegasi b. The planet is called 51 Pegasi b. We always give the b to indicate the planet, the first planet to be discovered. Sometimes you've got C, D, E as well if there's more. And this is the original data. This is a curve that shows you the radial velocity of this planet, of this star, excuse me, as a function of time. Time is not indicated on the axis. It's some measure of time. The orbital period is measured there. But the distance between these two excursions is 4.2 days. The amplitude of the signal is 50 meters per second. That's a lot larger than Jupiter and a lot larger than the Earth. That's why they could do this. That amplitude is consistent with a planet mass that's about half that of Jupiter, and it recurs every 4.2 days. So this is a planet the size or the mass of Jupiter, but in an orbital period, in an orbital distance that is very close to the host star, well within the orbit of Mercury. And so the reason this planet could have been observed actually probably already in the 1960s or 70s if they had looked. But this class of planet is so strange that it was not theorized that it could even exist. How do you get a gas giant planet to be so close to its host star? We have nothing like that in the solar system. Nowadays, we call these planets hot Jupiters for obvious reasons. There's a whole class of planets that are like this. 51 Pegasi is one of them. And there's a whole many more planets that are like this, very big planets in very close orbits to their stars. And the big advantage of this type of planet is, besides the fact that they exist so that we can study them, is that they have a very high probability of transiting. If you're closer to the star, the probability for being transiting goes up. And that means that once this planet or this type of planet was found using the radial velocity method, which doesn't care so much about what the exact angle is, immediately people started to search for transiting planets as well, because the probabilities of these planets transiting are a lot better. And so after 1995, it took only a few years before the first transiting planet was discovered. 51 Peg is not a transiting planet. It had a 10% chance of being transiting, but it wasn't. But quite quickly afterwards, the first transiting planets were found. This is the original data of the planet with the phone number HD209458b. And this planet was first observed with the radial velocity technique. That's the curve over here. Again, a nice sinusoidal curve indicating that the mass of the planet is about 0.64 Jupiter masses. And then it was found to be transiting. The periodicity I actually didn't mention it here, but it is about 3.5 days or so. And it was found to be transiting, and the transit depth, so the amount of light that this planet blocks, is about 1.5% of that of its host star. That's why I'm saying that you could almost do this with a smartphone, because that's a fairly large signal for people who analyze data. 1.5% is quite easy to observe, as long as you don't need a lot of stability to do. That corresponds to a planet with a radius of 1.4 times that of Jupiter. And this is actually very important because you've got two measurements that measure two different things. One of them measures the mass, one of them measures the radius. That gives you a very powerful quantity, which is the density. You can measure the average density of your planet. And that allows you to determine whether or not this planet is made of ice cream, let's say, or solid iron or uranium, right? In fact, it's very important because this is direct proof that this is a gas giant and not, say, a black hole or something very compact, right? This is proof that this is an actual planet. Now, if you know your densities, you'll know that Jupiter is about 1 gram per cubic centimeter. And you can already see it from the numbers, actually. This is a planet that's less massive than Jupiter, but larger than Jupiter. So its density is a lot less. That means it's very, we call it inflated. It's an inflated, puffy planet. Now, this discovery, or these discoveries, have started the exoplanet revolution. And since then, this field has grown to involve many thousands of scientists, many big telescopes that are being used, even telescopes that are dedicated to studying exoplanets being discovered, to discover them and to study them. And because of that impact, this was rewarded the Nobel Prize in Physics in 2019. And those two guys on the left-hand side are the ones who made the first discovery of 51 Peg. And they worked, one of them still sort of loosely does in Geneva, where I was also based for a few years. So that's a very big, process that these discoveries have set in motion. And nowadays, we find planets on very big scales. So we have a lot of telescopes all over the world. And if you're doing amateur astrophotography or amateur observations, these instruments will not look very sophisticated to you, and that's because they don't need to be. If you're doing transiting observations, at least, you can just make pictures, and the game is to make a lot of photographs of the entire, or a large fraction of the sky as you can, to measure the brightnesses of as many stars as possible at the same time. We also do radio velocities. For radio velocities, you do need bigger telescopes and you need stable spectrographs. Radio velocities are a little bit less efficient to obtain because you need to do one star after the other. With transit photometry, you can do thousands or even hundreds of thousands of stars at the same time, and that makes it such that we usually first detect planets using the transit method nowadays, and then we follow them up with radio velocities to measure their masses as well. That's how this process nowadays goes, and it's a very big industrial process where we observe these planets or these stars candidates now by the thousands, and it's just a matter of trying to follow them all up and measure very precisely how small the planets are that are in these systems. It's a very big assembly line of science almost. All right. We also have dedicated space instrumentation in order to do this. The Kepler Space Telescope has been the first dedicated exoplanet instrument to be launched in 2009. It observed 100,000 stars for 4 years, continuously, every 30 seconds or so. This telescope beams down a picture of 100,000 stars, surveying them for transit events, out to orbital periods that are a few years, because if you observe for 4 years, you should be able to see periodicities of 1 year or so, and it has been observing those types of planets. The TESS instrument, Transiting Exoplanet Survey satellite, observing from 2018 onwards, is an all-sky survey. It observes the entire sky in little chunks. So it takes these pictures, aiming at a certain slice of sky for 27 days. It aims at the same slice and then it moves on, and in this way scans the entire hemisphere, and then it flips over and does the other hemisphere. So it does one hemisphere and then another every year, more or less. And TESS has been finding the most planets, or starting to find the most planets by now. So much that I don't even know how many planets we know of today. I think it must be more than 5,500, but it changes every day because every day people are finding planets out of this test data. Okay, so this is a very important plot, which is essentially what we know. These are orbital periods of planets versus their diameter as measured by the transit method. And the axes, these are in Jupiter scales. So this is one Jupiter over here. These are like planets that are the size of Jupiter. And then these are orbital periods in days. And so these are your hot Jupiters over here, which have periods of a few days, the size of Jupiter, right? This is the class of ultra-hot Jupiter planets plotting over here. Below there is a glass of much smaller planets. They're also close in. In fact, all of these planets are relatively close into their star. Most of these have orbital periods of only a few tens of days. And so those are like Mercury's, but larger. Larger, the size of Jupiter, or 10% of that of Jupiter or something. Now, thanks to the rate of velocity method, we can also measure masses. So if you overplot in color the mass, you'll see that indeed these are heavier planets. They're bigger and they're also more massive. That's why they're whole Jupiter cloud. And these smaller planets are a lot harder to observe the masses from because their effect, these velocities that they make, are a lot less large. And so most of these planets, we don't really have the ability to really accurately measure their masses. Yes.
There are two clusters.
There's two clusters. Very good.
Why?
Why is there two clusters? This is a very good question. The question is, why is there two populations of planets? And the answer is physics. There is some physical process that makes the planets like to be here, and they also like to be down here, but they don't like to be in the middle somehow. And this has to do with how these planets form, or rather how they evolve after they are formed. Planets on this, if a planet would form here, it is hard to be stable. It likes to, if it's big enough, it will survive so close to the star. If it's not so big, the stellar radiation will cause it to lose its atmosphere, and it will shrink as a result until it's down here. So this is the effect of some form of evolution that's happening to our planets. Just by observing thousands of planets, by discovering them, you can already start to learn something about the physics that's taking place. We call this the evaporation desert, because planets don't like to be there.
So would you call them all these to be Jupiters? In fact, I mean, they are changing in size and you know.
These are called hot Jupiters.
Yeah, they are.
These are called hot Neptunes.
Neptunes.
They're sort of the size of Neptune.
What do you have the Earth?
Very good question. That's my next slide. Where you have the Earth is right there. And Jupiter is up there. Jupiter is actually the type of planet that we can already start to find with the rate of velocity method mostly. But these are a handful that actually, by chance, transit. The Earth is down here. And we haven't found any planets over here. That's not because they don't exist, but because they are not yet observable. Question?
Why don't we have any planets like right at the bottom?
Over here.
No, on the right side.
Here.
Yeah.
Yeah, over here, because the transit method, in order to apply it, you would have to wait for thousands of days to establish that these are repeating. And also the signals get quite small. Once your planet is not the size of Jupiter anymore, but it's a lot smaller, then you do not actually have these very strong signals anymore. And it becomes more difficult because your signals are smaller and they occur much less frequently. And that is the technological problem that we're dealing with. So this is an observing limit. It's very probable that this entire region is filled with all sorts of planets that are like the solar system. The fact that we have observed a few planets here just by chance indicates that there must be many planets like Earth. We just can't observe them yet. So the game is one of technological improvement. We are improving our telescopes in order to fill in this part of the diagram and to observe planets that are more and more like the solar system.
Well, you said Earth. I'll put one Jupiter diameter is about what Earth is, but orbital period of 2,000 days.
Oh, I think I made a mistake in my axis. Yeah, that's a very clever one. So there's clearly a problem in the axis. I think I've skipped the 100. It goes 1, 10,000, 10,000. You see that? This must be 1, 10, 100, 1,000. Very, very clever. Yeah.
So that number should be a tenth of what
that's true. The 10,000 is over here. Very nice. Very clever.
Yeah, because Earth has
300 and not 3,000 days. Exactly. Very good. Yeah. Yeah. Sharp. Stay sharp. Okay. So you can make another type of plot because we measure radii and we measure masses with these two techniques. You can measure plot those against each other, and that has to do with the density, right? And so if I would take my rate of velocity planets that are also transiting and I would plot their mass versus radius, I can see that these populations also separate a little bit. And that has to do with what is the typical composition of our planets. So planets that are like Jupiter have a density that is corresponding to the density of hydrogen. If I have a ball of hydrogen that is 100 Earth masses heavy, then it will get a radius of about 10 Earth radii. But if that same 10 Earth masses was rock, the planet would be a lot more compact. It would be a lot smaller, and it would come down here. So these are your gas giants, which are made of hydrogen. And some of these planets that we're discovering, this is not all of them, this is only the ones that have small errors, I believe. You start to see that they sort of move down towards lines that are consistent with rock or iron or water. And so planets that are down to about 10 Earth masses, which we don't have in the solar system, right? Those would be rocky. We observe planets that are that big, large, but they're still made of rock. There's also planets in between, where they're not really gas giants and they're not really rocky either, and they're sort of in between. And they're also like here, where they may be like the density, like the Earth would plot down here. They're like a little bit less dense than the Earth, mixing in perhaps a lot of water, but not being gas giants either. So there's these in-between planets that exist, and there's a lot of those, which we don't really understand at all. We don't understand what a 5 Earth mass planet looks like at all. What it's made of, if there's water there, how does it behave? If it has an atmosphere, what does it look like? Those are the types of questions we're trying to answer. In fact, all of the planets, I would argue that all or the vast majority of the planets that we've discovered are strange from our point of view, because they're not like Jupiter, they're not like the Earth or Mars or Mercury. Maybe they're a bit more like Uranus and Neptune, but then they're very close in and very hot. And so what does that mean? All of the planets that we observe, we don't have an intuition for what they might look like. All right. Now, a question that you should ask yourself is, why do we have these planets in the first place? All of these planets that we are observing are so close to their host star. Why don't we have a planet like that? We have Mercury at an orbital distance of 33 days. That's even quite far away from my point of view. Right? Why do we have these planets in the first place? How do they form? And for that, we need to quickly have a quick look at planet formation theory, which was not understood very well in 1995 until the first hot Jupiters were discovered, but it's better understood now. So planets tend to form in what we call a protoplanetary disk. For about 5 million years since the formation of the star is surrounded by a disk of material, gas and dust, which contains the material from which the planets form. They coalesce inside these rings to slowly eat up the material that the disk is made of. At some point, the star ignites and it blows away any remaining gas, leaving the planets in their orbit. That's why all the planets orbit more or less in the same plane, because they came from the same pancake-shaped disk in the very beginning. Now, this is an artist rendering. We also simulate this in quite a lot of detail. This is a hydrodynamical simulation of how gas and dust behaves in a disk like that. And you can see that a density forms where ultimately a gas giant is going to form. An overdensity forms, and this material starts to gravitationally influence the other material in the disk, creating this beautiful spiral wave. It also clears, this dark region is where there's no longer any material, clears the disk of material too. So it creates a gap, what we call. Now, these spiral structures actually pull the planet. The planet pulls the material, but the material also pulls the planet. And this has the effect of moving the planet inwards. It's like the star or the gravity is vacuuming this planet inwards towards the star. Now, this takes a certain amount of time. And if the star would disperse the disk before the planet is eaten by the star, right before that moment, the disk is cleared, the effect goes away, and the planet might be stuck in a very close orbit around its star. Maybe the solar system had a planet like this. A planet like Jupiter forming closer in, being tugged in, and being eaten by the sun before the disk was disappeared. We have no way of knowing. It's possible that has happened. And for some small fraction of stars, the planets just happen to almost make it, basically just barely survive. Those are our hot Jupiters. This is one way of making hot Jupiters. There's other ways too, where planets interact with each other gravitationally, and one of them gets sort of flung in to go into a very short orbit. That's also possible. So we have now theories that explains that very naturally. Actually, it's very, very easy to understand. You don't need to do very complicated math in order to figure out that this happens. But in 1995, this was just not on the radar. This was just not thought about.
These hot Jupiters, do they in the middle have as to say a small rock
Yes.
border is size as Earth or
Yes.
something like that?
We believe that the interior structure. So the question is, what do the hot Jupiters have cores, like rocky cores as well? The answer is yes. We believe that because of the way that this planet starts to form, at first it creates rocky material and then it starts to suck in gas. So you always have a rocky core. That's the idea.
If it only was gas that big and hot,
yes,
it would evaporate.
I suppose. Then again, brown, yeah, maybe.
But a stone or iron ball in the middle.
Yes, that's right.
Would make the gravity.
We would need that in order to start forming the planet in the first place.
Yeah, I was just thinking about all the red dwarf stars, which are actually the most of the stars are red dwarfs, small ones, and now they have found.
I will talk about.
Yeah.
Very good. All right, so
hot Jupiter there.
Yes. Now, this is of course theory. This is a simulation. We can simulate anything in our computer, but we can also observe this. So, here we go. These are actually quite old observations of protoplanetary disks observed in Orion. Hubble Space Telescope images showing that a lot of these young stars are surrounded by dusty disks. So it's not so new. This whole idea of planet formation in disks has been observed and studied since Hubble, really. Also, nowadays we have the ALMA telescope, which is a very short wave radio array that can make very beautiful pictures of dust in these protoplanetary disks, including the ring structures that we theorize should exist because planets create these gaps. So we are starting to really observe this processes. That's not very easy. You need big radio arrays, but we have now the ability to study many of these young systems as the planets are forming inside them. All right. So preliminary conclusions. The exoplanet population is diverse. Most planets that we know about do not exist in the solar system. These are all strange and extreme planets in their own right. And finally, planet formation is complex, but can be observed and understood. And planet formation being complex gives rise to this big diversity of planets that we have. It already indicates the fact that you have so many different types of planets indicates that this is not a single process that's happening, but you must have many competing processes, like, for example, evaporation, shaping what planets look like. It's not so straightforward, but we can observe planet formation, and we can also learn more about our planets themselves, and that's what I mostly study. When I do my own research, I don't discover planets, but I try to study them, and mostly I try to study their atmospheres. And again, in order to do that, we use spectroscopy. And the theory is very simple. If I have a light source, say a star, and there is something in between, if that is gaseous and the light makes it through, I can observe spectral lines. And from those spectral lines, I can determine what the gas is made of. That's all we do, mostly at least, in a lot of observational astrophysics, is observe spectral lines of gas. And so for our planet, when it is transiting, the atmosphere that surrounds the planet goes in front of the star. That starlight gets absorbed a little bit by the gases in the atmosphere. And from the spectral lines that appear during the transit, we can then observe what the atmosphere of the planet, and by extension, perhaps the planet itself, is made of. All right. If you look at this from the side, it looks like this. So I have an illuminated side of my Jupiter. In my case, it's a hot Jupiter. I mostly study hot Jupiters. The light that makes it through the very edge or along the very edge of the atmosphere is then going to be absorbed depending on what the atmosphere is made of. So you might observe lines of hydrogen or of carbon dioxide or of water in the atmosphere, and those will appear in the spectrum when the planet is transiting. And when it is not, the spectrum is not there. So we take a difference measurement. We compare the system before, after, and during the transit event, we subtract them. The lines that are then remaining are the ones that are from the planet. Now, some light may also be scattered here. Some light might, in fact, also be absorbed. If the planet is all cloudy, then we don't see anything. The same for the Earth's atmosphere. You cannot observe on a cloudy night. You don't see much on cloudy hot Jupiters either, or cloudy planets either, for that matter, because clouds have a tendency to block all of this light. And so clouds are a very big problem in our field. When a planet is cloudy, it's not good, because then you don't see anything in the spectrum. Here's an example of what this data looks like. So just to make sure that you read this graph the right way, absorption is up. So less light as up spectral lines are plotted in that direction upwards. And this is a spectrum observed with the Hubble Space Telescope. These data points are all from Hubble. And there's 2 data points here from the Spitzer Space Telescope as well in the infrared. And so very typically what you observe for a hot Jupiter, this guy is called WASP-39b. It has a temperature of about 1400 degrees centigrade. And what you very typically see is this very strong feature of water. Water absorbs at 1.4 microns or 1400 nanometers. And this feature is by water vapor. At 1400 Kelvin, you have water, and it absorbs at this wavelength. And we can nicely observe that. We can also model it. So we make models of the exoplanet atmosphere at a certain temperature with a certain composition, including a lot of water. And then we can measure, for example, how much oxygen is there in this atmosphere, right? You also see absorption lines often of other things, like, for example, sodium. At 1400 kelvins, sodium is atomic in gas phase, absorbing very strongly at this wavelength, this nice orange wavelength. And there it absorbs, making the planet look a little bit bigger, actually. So we can now start to ask ourselves, how much sodium is there in our planet atmosphere? If planets form in this or that way, what does that mean for how much sodium there would be? And so we can link these types of observations back to planet formation processes, because one planet formation theory or another might have something to say about how much oxygen there is or how much of sodium there is in our planet atmosphere. As I said, this was done by the Hubble and Spitzer space telescopes. Spitzer is no longer active. It was retired. Hubble is still active, but it's been there for more than 30 years or so, and it is slowly degrading. This telescope will no longer exist in a few years. But of course, the big new kid on the block is, of course, the James Webb Space Telescope that we're all very excited about. James Webb has recently, well, already 3 years ago, actually, been launched. It is a gigantic 6-meter mirror in space that is constructed out of these segments that have been folded up in a rocket. A 6-meter mirror cannot fit in a rocket because rockets are not that big. So they had to unfold it in space to make this whole thing the size that it is. It also has a very big, complicated array of heat shields that is necessary to protect it from the sun's radiation, because this is an infrared telescope. It's sometimes thought to be the successor to Hubble, but that's not true. It's more the successor to Spitzer, because it's an infrared telescope. And when you observe in the infrared, your telescope needs to be cool. That's why it has these heat shields, and Hubble doesn't. The same planet was observed with James Webb. Oh, wait, first of all, why is James Webb a big deal? Well, here's why. You have Hubble image of the pillars of creation, that cloud, and it's a star-forming region as well. You make stars and planets in these little dense regions. And when you observe the same thing with James Webb, you can clearly see that there's a lot more detail. But mainly what you see is that these clouds become transparent in the infrared. The reason you observe in the infrared is because you can peek through the clouds. And so we can look inside of these cloudy regions that you could not do with the Hubble Space Telescope. That's the main reason why we actually really, really like James Webb Space Telescope. Also, this is good news for our clouds in our exoplanet atmospheres, because that's also dust that we can look through better if you look at infrared wavelengths. I've got another example. This is for a planetary nebula, where you can clearly see there's a lot more detail to be observed with this new telescope. And all fields of observational astrophysics are being revolutionized, almost all fields, by James Webb. Now, the same spectrum of the same planet was observed with James Webb, and the color data points are James Webb points. These black points still over here are Hubble, and you can clearly see what a difference this makes. This is the revolution of exoplanets happening in front of our eyes, because now suddenly we can observe a lot more wavelengths with a lot more precision. This here is the first observation of, or one of the first observations, no, the first observation of carbon dioxide in any exoplanet. We knew that this band of absorption by carbon dioxide is there. Of course it's there. That's why we have the greenhouse effect on Earth. We knew that, and models have always predicted that. If you go back a few slides, here is a very big band of CO2 predicted by models in 2018 before it was observed. But now we can actually observe it with very high precision. There's another bump here by SO2. We did not know that would be there. We did not predict that, but it was observed. And we now know something more about chemistry in exoplanet atmospheres. This is a groundbreaking discovery. So James Webb is really changing the game as to what we can observe in exoplanets and what we can learn. All right. Now we're running a bit out of time. I hope that's okay with you. It's okay with me. I'm just getting started. No, that's not true. I've got about 10 minutes more. So hot Jupiters are great. I observe hot Jupiters. That's my career. But a lot of people and a lot of astronomers are ultimately not so much interested in hot Jupiters because they are so extreme and hot and interesting, and because there's all these things in their atmospheres. Ultimately, this field is moving towards smaller planets that are less like hot Jupiters and more like the Earth. We are trying to observe, ultimately, Earth-like planets and potentially even habitable planets. That's where this field is ultimately headed. Now, there's a concept in habitable planet theory, which is the habitable zone. That is that if your planet is too close to the star, it's too hot. If your planet is too far away from the star, it's too cold. So there's this region in between where temperatures are just right, such that you might imagine there's life like that on Earth. The criterion that's often used is that liquid water is necessary. So you need to have a temperature between 0 and 100 degrees, and that is the correct region within which your planet could be then potentially considered to be habitable. Habitability is a very problematic concept, and I'm going to explain to you why in a bit. The problem is with any star that's like the sun, and here now we're going to go to our different types of stars, but any star that's like the sun, a planet like that will have a period of about 1 year. And as you have seen, those are not very easy to discover. We don't discover those planets very well yet. It's just technologically very difficult. But there's different types of stars. And so what we're going to do instead, and what we have been doing for the past 10 years or so, is to specifically target stars that are much smaller than the sun. M-type stars are much less luminous, therefore their habitable zones are much closer in. And so since we're good at observing very close in planets, for M-dwarf stars, those might actually be planets that are close, that are in the habitable zone and observable with our current techniques at the same time. That's the solution to the habitable planet problem today. You can't find Earth-like planets around the sun. Well, maybe we can find Earth-like planets around M-dwarf systems, and the answer is yes, we can. And one of the most famous systems where this has been done is called the TRAPPIST-1 system. TRAPPIST-1 is named after the survey. It's a Belgian survey that was named TRAPPIST. It observed or discovered one system called TRAPPIST-1. There was no TRAPPIST-2, one system. But the system that it did discover in 2015 or so was very unique and exemplary of what we are now trying to do. This system is a system of exoplanets that are all more or less the size of the Earth. There are 7 of them, and they're all transiting. Here is the transit light curve observed by Spitzer, I believe, when it was still active. And this is the brightness of the star, this cloud of points. And in between, you see these dips, these little streaks that go down. Those are all transit events of different planets. There are 7 transiting planets in the system, transiting one after the other. So this makes the data quite complex, but you can disentangle them. And they all have different depths because all these planets are a little bit different in size. And this was a revolutionary discovery. The system is about 40 light years away from Earth. So in astronomical terms, it's not that far away either, but it's not so easy to observe because the M star itself is very faint because it doesn't emit a lot of light. So technologically, it's still quite difficult to actually observe this. You can also not really do it with visible light telescopes. You need infrared telescopes mainly to do this. Comparing this system with the sun, it is very strange again, because all these planets are compacted very close to the star. This is a 2-scale representation of the inner solar system, where all of these planets are orbiting very, very closely. And you kind of have to scale the whole system up to compare it with the solar system. But then there is this line, this array of 7 Earth-sized, more or less, planets, all transiting very closely to its star. And if you overplot the habitable zones of these 2 systems, you can see that there's not 1, but potentially even 3 planets or so that might be candidates for habitability. And this has astronomers very excited. Because if one of them may be not habitable, the other 2 might. So there's been a lot of observations of these planets, including by the James Webb Space Telescope, who's been observing this system really a lot of James Webb observations have been done to the system to try to figure out what are these planets like. Are they really Earth-like? Because they have the same size and mass as the Earth does, but what does that mean? So we're trying to figure out their atmospheres too. And this brings us to a little bit the problem of habitability. The habitable zone concept is a concept I don't like very much. And the reason is that it doesn't really work. Because, for example, Venus is an Earth-like planet in all respects. It's very Earth-like. It has the same mass and radius as the Earth. It's also orbiting in the habitable zone of the solar system. But it's very far away from being habitable because of what the atmosphere is doing. The atmosphere is making the difference. And so you can find a planet that's Earth-like, but it doesn't mean anything unless you have observed its atmosphere because of the greenhouse effect. In the case of M-dwarf stars, there's more to be concerned about, besides the fact that you don't really know anything about your planet unless you've observed the atmosphere, which is quite difficult for Earth-sized planets. There's the fact that M-dwarf stars are very active. They have a lot of flaring events, a lot of X-ray radiation that comes off of these stars, and that might be hurtful to the atmospheres, actually. So it's quite likely that these atmospheres have a hard time staying because they might evaporate away from the planets at a high rate. In the same way as Mars actually used to have an atmosphere and liquid water on the surface, we know that for sure. That atmosphere was lost because the Earth's the solar wind has stripped Mars from its atmosphere because Mars was too small. Its gravity was not large enough to retain the atmosphere. And we believe that this might actually happen quite efficiently in these M-dwarf systems. So even though the M-dwarf planets might be very observationally favorable, it doesn't mean that they're going to be in any way habitable because they might simply not have atmosphere. And there's more to be worried about because when you place a planet very close to its host star, it has the tendency to synchronize. It has the tendency to tidally synchronize its orbital period with its rotation period in the same way that the moon is synchronized to the Earth. And you always see the same side of the moon because the moon's orbital and spin periods are the same. These planets will have that too. So you'll have a side of the planet that's very warm and a side of the planet that's very cold. And that might not be good for atmospheres either, because if it's very cold on the night side, maybe all of that atmosphere might freeze and collect there. And so you might have all sorts of gases like CO2 and nitrogen just freezing out on the night side because it's not warm enough. This is also possible. So there's a couple of reasons why you might not like these potentially habitable planets, because you need to really worry about a couple of effects that other types of planets might not actually suffer from. So, conclusions. Yes, question.
There are some ideas that the Earth would not be habitable without the moon. And if that's correct, if you want to find a habitable planet, you will search for one with a moon, a large moon. Is that possible?
So the question is, don't you actually need a moon in order to have habitability too? Isn't that a problem? Well, the answer is I don't know. It's sure that the Earth's evolution would have been very different if there was no moon, but that does not mean that generally speaking you need a moon to have habitability. It's hard to say that. Let's see. Yes, another question.
Some weeks ago, I asked Peter actually a question that is a bit related to what we have been talking about, but you have not come in to it specifically. One thing is that you're studying the chemistry and the temperature and atmosphere, what it consists of, but there is also things like radiation that need to be protected for to actually be able to be in a habitable zone and also contain life.
Perhaps.
Is that something that anyone is actually studying?
So the question is, don't you also need to worry a lot about the radiation environment?
No, it's not always there anyone studying.
Oh, absolutely. Yes, of course, for sure.
Because
some people's, well, because there's not too much to discover. There's exciting research going on. You might think that if you have a lot of radiation, it's bad for life, but actually it may also be good for starting life. If you want to do biochemical reactions, you may need harsh radiation to get those molecules to break open and do more complicated reactions. So it may actually be good to have strong UV irradiation in order to start life, at least.
That would be very volatile.
Who knows?
Probably.
Who knows? We're starting to inch into the last minute of my talk, which is about life, because I promised you I was going to say something about life. The conclusion right now is, and this is the state of the field essentially, we can detect many planets, including Earth-sized planets in habitable zones. But we don't know much besides sizes and masses. And the habitable zone that we're talking about may in fact not be so habitable at all. And I'm not going to show you the graph because it's a bit difficult to explain exactly how it is plotted in the paper, but only a few months ago, James Webb Space Telescope observations of TRAPPIST-1b and C came down, indicating that these planets may indeed not have atmosphere at all. They may be more like Mercury than they are like the Earth. We're still waiting for the other planets too, and those are a bit more difficult, so it takes more time, but there's already indications that our current observations are going to perhaps drive us away from this focus on M-dwarf planets, and we need to go to the solar system planets after all. The sun-like planets after all. And what we need for that is very big telescopes. So this is the ELT, which is currently being constructed in Chile. First light is expected about 4 years from now in 2028. This telescope is enormous. That's why it's called extremely large, with a mirror diameter of about 39 meters. Again, this is so large that you cannot make the mirror out of a single piece. You need to have it segmented into tiny different pieces. This thing has hundreds of segments. And this is a nice artist rendition where I think somewhere down here you can see a truck. So this is a very, very large construction. And this is not fantasy. This thing is actually being constructed. Here's a webcam image that you can look at any moment. I looked at it yesterday. As of yesterday afternoon, the construction site looks like this, where they really are already starting to construct this dome. And so I believe they are actually on schedule for delivering this massive telescope in 2028. And this is a European endeavor. The Americans are not building anything like this. The Chinese are not building anything like this. This is really European, a collaboration of 27 or so member states of the European Southern Observatory banding together to make a project of this size work, which is a very, very important, I think, achievement. This telescope will be the biggest telescope on Earth for decades, most likely, the way it's going. And so Europe is really at the forefront of ground-based spectroscopy, ground-based astronomy in this regard.
Hooray.
Hooray.
Right. Hurrah. Yes, Europe works. It does. Also, we've dedicated other... No, I'm not finished. One more minute. I promise you. We've dedicated space instrumentation that's coming as well. Plato, Ariel, both European, by the way. And the whole goal of these missions is to fill in that little gap. Now, the one thing is that what I want to do is talk about life. I have no clue. People sometimes ask me, is there life out there? There must be, right? There are so many planets. How can there not be life? The answer is we really do not know whether life forms out there or not, or what it looks like. So this is a question I have no clue about. We tend to believe that there is because we have constructed this image of extraterrestrial life for ourselves. I was in the bathroom just now, and there's all these pictures that children have drawn about what life might look like. We have imagined life to look a little bit like this in various forms or another, and this leads us to a dangerous path because it misrepresents potentially what I think life is going to look like. Because we've imagined this, we've searched for life like this. So we build these big radio dishes to search for extraterrestrial communication, radio, or nowadays they talk about airport radars, which you can also observe across interstellar distances. But this is a little bit dangerous because it underestimates the scale and size and time scale as well of things that happen in the universe. And this only really dawned to me only a few years ago, how actually this is misleading and how thinking about extraterrestrial life in human terms is a dangerous thing to do. Because if you look at them, this is the last slide that I have, the single last slide I have. If you look at the time scale of life on Earth, and now this is about looking backwards rather than outwards, if you look at how life emerged on Earth, Earth has been a living planet for 3.5 billion years. This is a wheel that counts time from 4.5 billion years ago all the way until now. And dinosaurs are like here. So all of Earth's history, there have been no dinosaurs. Mostly there have been plankton, algae or something. And humans are all the way here. In the last 2 million years or so, you can speak of humanoid life on Earth. 2 million years is a blink of an eye compared to the lifetimes of stars, right? So 3.5 billion years ago, until about 500 million years ago, it's been like this. If I think about extraterrestrial life, it's probably going to be like this. maybe it's going to be a little bit like this. If I think about chemistry of my exoplanet atmosphere, it may be influenced by this type of life out there. And only for a few million years or so, it's actually looked like this, with devices that we're using, and nowadays we're flying to the moon and etc. And this little bit of evolution of life on Earth has taken place in only a few years. And so this is a blink of an eye compared to all of the stars that are out there. And if you imagine a living planet that has formed at the same time as the Earth did, plus minus a blink of an eye, you should ask yourself the question, what's plus 1 million years? There's no reason why any life that we observe that is about as old as we are might not be 100 million years older than we are. And that does not look like that. So there's a 50% probability. That's my answer to the question of life. There's a 50% probability that life looks like this, which is not so interesting. For me, it's very interesting because extraterrestrial algae are super interesting. But we don't think about it as interesting, right? The other 50% is that life looks like that. We have no clue what that is like. We have no idea at all what this guy looks like in a million years or what that thing looks like in a million years, right? No conception whatsoever. And so 50-50. If there is life out there. If there's no life out there, this is not even a valid discussion. But if there is life out there, it's either going to be like this or like this. And that's the last thing I wanted to say. Thank you very much for your time. I don't know how you want to do the question, because we're a bit over time. We can hang out a bit, but
I'm sure that we have some time for questions.
If you want to leave, you should not feel embarrassed. Please go if you need to be somewhere. If you want to
taxi arriving.
Well,
so that was the reason. I see. I think you have already made your quota of questions. So we'll start with you.
It's interesting. Your research. What kind of data? Where do you get the data for your research?
So I observe mostly hot Jupiters, as I said, and I do so with spectrographs that produce spectra that have high spectral resolution. So I use the shell spectrographs, and I measure metals in the atmospheres of these very hot planets. So if you have a planet that's more than 2000 Kelvin, you will get iron, titanium, other types of metals in the gas phase. And they produce a lot of lines that we can observe quite well. So I'm the metal person, actually.
Metal guy.
Yeah, metal guy. We do start the share. Start the share. Yeah.
Okay. Another question then.
How old are those stars that you are studying?
Sorry, how?
How old are those?
Right. So to make your planet very hot, it helps if the star is also very hot. And so the stars that I typically observe are A-type stars, and those have shorter lifetimes than the sun does. So these massive stars will typically have lifetimes of like 1 billion years or so, versus the sun that has 10. So typically like 500 million years. These are actually not even systems where you might think that you could evolve life in if you had Earth-like planets. But simply because the stars need to be hot to get these planets to be so hot as well, those are typically the stars that I look at. Yeah.
I was thinking about the distance is of course a problem, but if you look at the closest star, Alpha Centauri is some more than 4 light years away. Sirius is at 8.6 or something, and within 10 light years there is a couple of stars. I think how much have studied those stars?
So this issue with so there's 2 problems. First of all, we can't detect Earth-sized planets even if they are close by. It's just not really doable. Besides Proxima Cen-b, which was very difficult to actually observe. It took many years to get that curve. The hot Jupiters are a fairly rare class of planets, even though I like them, especially the hot ones. They are super rare planets. There's only a handful of them out of those 5,000 or so. They're very rare, and they have a transit probability of about 10%. So that means that about 0.1% or 0.5% of all stars will have a transiting hot Jupiter. And so that puts you already further away than 10 light years. So it's just a combination of you need many stars in order to find these planets that we can discover right now. And the better we get at discovering planets, the more closer in our discoveries become.
I think I heard probably a star around Centauri, Alpha Centauri.
Alpha Centauri B was a proposed planet that I believe has been decided was not. It was the star itself is also active, and that actually puts a barrier on how small you can go, because the sun itself as well, will pulsate by about 10 or 20 centimeters per second, and that just makes it very difficult to actually see these Earth-sized planets.
I have a couple of astrophysical questions, I suppose. I mean, these hot Jupiters, if you study the correlation between the frequency of those and the type of host stars, do they have a favorable host star? I mean, are there hot Jupiters around M dwarfs, red dwarfs?
I think that this correlation is weak.
Okay.
It's not exactly known. It's weak. It is known that stars that are more metal rich have more hot Jupiters, which I think you can understand. If you have more material to go around, then it's easier to make gas giants. So you have more gas giant planets around metal rich stars. But also that's a weak correlation, actually.
Another possible point about these planets around M dwarfs, they are tidally locked. Are they possibly also tidally massaged like the Jupiter moons?
Yeah, that's a good question.
Has that been studied?
This has been studied, yes. Yeah. I don't know the latest. The TRAPPIST-1 system is an astrophysical community on its own, because there's so much being studied there. I know of some planets that definitely are massaged, volcanic planets. I'm not so sure how extreme this effect is in TRAPPIST-1, but it might actually contribute to producing an atmosphere, because if you have a lot of volcanoes, you produce a lot of gas, and so who knows? I'm not sure what the latest is on that. I guess we don't really know, because it's very difficult to, like, geology on the Earth. If you want to do geology on the Earth, what you need to do is you need to walk around and study rocks and place seismometers and do these kinds of things. If you cannot do that, you basically don't have enough constraints to say many interesting things, intelligent things about what the geology is. Rather, you could theorize about what it might be. Depends also a lot on what these rocks are actually made of. If they're iron rich or more magnesium or silicon rich, that also changes a lot how this works.
Okay, 2 more questions. Yeah.
I read somewhere that they are started to be very interested of K stars, because they are slightly smaller than the sun.
Right.
And maybe that's...
Yeah. You're trying to find a sweet spot. So the M dwarf planets have all sorts of problems. The solar type stars, it's just too difficult, so you go in between. That's indeed the K dwarf, what's called the K dwarf opportunity, I think. There's a word for it, yeah.
With the ELT, the European Extremely Large Telescope, what would you expect on it in your own speciality?
The moment you make any bigger telescope than there has been, you will suddenly be able to observe groundbreaking new things. James Webb has shown you this. ELT is showing that as well.
This is always happening.
This is always happening. That's why I'm excited. In 4 years, I hope to be using the ELT myself.
So the problem is that you don't know what you will be.
I don't know, right? But I can predict, and that is that. First of all, like the thing is also a bit with James Webb. The moment that we build a bigger telescope, that's when we start to observe TRAPPIST-1 a lot more, and then we find out later that maybe that wasn't such a good idea because they don't have atmospheres, for instance. We usually discover that after the fact. James Webb is I think that James Webb is a hot Jupiter machine, and it's shown us interesting details in the atmospheres, like differences between one side of the planet and the other, and you see differences in chemistry and how the gas is flowing around. Those are signals that are very interesting if you are after the details. How does this climate work? And the ELT is going to do that another step greater, especially in my own field, because I work with high resolution spectrographs. James Webb doesn't have any, but the ELT will have. And so Sweden is also participating in shell spectrographs. Yeah, Sweden is also participating in building some of those, and so we are in the game when it comes to these kind of observations. Yeah.
Okay, I suppose that's it. So if you will just be kind enough to pass me that little thing I have over there.
You mean this one? Yes.
Yeah, exactly. Thank you very much. Somebody, I don't know why they're laughing, but they might know a little bit about what I'm going to tell you.
Yeah.
So I will, you know what, I will just do that, something like that. Yeah, it's not that necessary. Okay. So, thank you very much.
Yes, thank you.
I did inquire about your Swedish level, and when you have read this through, I'm sure it will be a little bit better.
Yeah,
so,
well,
it's about Swedish astronomy history,
okay.
And I hope you will.
Thank you very much. I plan to stay in Sweden for a lot more.
So thank you. Okay. Excellent. Thank you very much. So we will close down this meeting. I can do that.
Thank you also for people online.
Yes.
Thank you for sticking around.
Okay, can you get up here? Ja, det är sant. Jag tackar er också där ute. Och så ses vi snart igen. Det är nästa möte är vårt årsmöte. Det får ni hemskt gärna hålla reda på och se till att komma. Tack ska ni ha för detta. Tack, hej på er.